Hello, welcome. In this short video, let us look at the properties of the gamma function. So in this video, we are going to look at some properties of gamma function. The gamma function is defined as gamma of t is equal to 0 to infinity x power t minus 1 e power minus x dx. The first property we are going to look at is gamma of n plus 1 is equal to n times gamma of n for all n not equal to 0. So by using the definition of the gamma function, we have gamma of n plus 1 is equal to integral 0 to infinity x power n plus 1 minus 1, so x power n multiplied by e power minus x dx. That is, when we replace t with n plus 1, it becomes x power n. Now we can rewrite the integral as limit p tends to infinity integral 0 to p x power n e power minus x dx. Now by applying integration by parts on this integral, we have limit p tends to infinity. So the first function will be written as it is, and then we have the integral of e power minus x, which is e power minus x minus 1 over minus 1, and the limits are 0 and p. And the second component is minus integral, and x power n we write the derivative of x power n, so it is n times x power n minus 1 multiplied by integral of e power minus x, which is e power minus x by minus 1 dx, and again the limits are 0 to p. The first term clearly is equal to 0 because for the values of x equal to 0, clearly the term is 0 because this is 0 power n, which is 0, and e power 0 is 1, so 0 into 1 is 0. And for the second value, or the second limit p, we have p power n into e power minus p, and for the limit p tends to infinity, the function e power minus p is clearly going to be 0. So the first term under the limit p tends to infinity is clearly 0. The second one is limit p tends to infinity into n times integral 0 to p x power n minus 1 e power minus x dx, which is clearly equal to n times the gamma function of n, that is gamma of n, by using the definition of gamma function. Therefore, gamma of n plus 1 is equal to n times gamma of n, and of course for all values of n not equal to 0. And this relation is not valid for n equal to 0 because from the definition of gamma function, for n equal to 0, the value of gamma function will be equal to 1, as we will verify shortly. But by using this formula, gamma of n plus 1 is equal to n into gamma of n, it will give a value of 0, which is not true. So this property is only correct for n not equal to 0. The second property is gamma of 1 is equal to 1. This can be simply verified by using the definition of gamma function, integral 0 to infinity x power 0 e power minus x dx, which is e power minus x over minus 1, the limits 0 and infinity, which is clearly equal to 1. Because for x equal to infinity, this is 0, and for x equal to 0, this is e power 0, which is 1, and we have minus 1 here, and this is the second limit, so this should be equal to 1. Therefore, gamma of 1 is 1. And the third property is gamma of n plus 1 is equal to n factorial for all values of n that belong to set of positive integers, that is natural numbers. Now let us verify this property by using mathematical induction. So for n equal to 1, gamma of 1 plus 1, which is gamma of 2, and we know that gamma of 1 is equal to 1, and by using the property gamma of n plus 1 is equal to n times gamma of n, we have gamma of 2 is equal to 1 into gamma of 1, which is again equal to 1. And by using the right hand side, that is n factorial, and by using n equal to 1, it is equal to 1 factorial, which is equal to 1. Therefore, the proposition gamma of n plus 1 equal to n factorial is true for n equal to 1. Therefore, for n equal to 1, gamma of n plus 1 is equal to n factorial. Now let us verify the relation for n equal to 2. This gamma of 3 is equal to 2 times gamma of 2 by using this property. Gamma of n plus 1 is equal to n into gamma of n. So this means this is 2 times gamma of 2, which is equal to 1. So gamma of 3 is clearly equal to 2. And from the right hand side, gamma of 3 should be equal to 2 factorial, which is equal to 2. Therefore, for n equal to 2, gamma of n plus 1 is indeed equal to n factorial. This the relation is verified for n equal to 2. Now let us assume that it is true for n equal to m. That is, let us assume that gamma of n plus 1 is indeed equal to m factorial. Now we have to derive that it is also true for n equal to m plus 1. That is, by replacing m with m plus 1, we have gamma of m plus 2, which is equal to, by using this property, it should be equal to m plus 1 multiplied by gamma of m plus 1. And by using this result, it should be equal to m plus 1 multiplied by, and we multiplied by m factorial. That is, we replace gamma of m plus 1 with m factorial. So this is equal to m factorial. And then when we multiply m factorial with m plus 1, the result is m plus 1 factorial. Therefore, the relation is proved for m equal to m plus 1 because gamma of m plus 1 plus 1 is equal to m plus 1 factorial. That is, when the relation gamma of n plus 1 equal to n factorial is assumed to be true for n equal to m, it implies it is also true for n equal to m plus 1. And since the relation is true for n equal to 1 and 2, and it is also true for m plus 1 given it is true for n equal to m, basically this proves that gamma of n plus 1 is equal to n factorial by mathematical induction. Of course, for all values of n that belong to the set of natural numbers. Thus, to summarize, we looked at three properties of gamma function. The first one is gamma of n plus 1 is equal to n times gamma of n for all values of n not equal to 0. And gamma of 1 is equal to 1. And gamma of n plus 1 is equal to n factorial for positive integers, that is natural numbers. Thanks for watching.